right, here we go. So section 21 is on angular and linear motion. Okay, so yesterday we kind of talked about radians. We're going to use radians today. We're going to talk about revolutions per minute and so on. So the first example says the second hand on a clock is 5 inches long. How far does the tip of the second hand move in 45 seconds? Oh, is it not on? Can you guys stand up there and turn it on? All right, so what we're going to do is we need to think about how many degrees it's moving in 45 seconds. So go ahead and draw a little clock on your paper.
Did you seriously say?
It's like on the opposite side of the power light. All right, so if you talk about how many degrees it's moved in 45 seconds, can anybody tell me that? So 3/4, so 360 degrees. Exactly, so we're going to have 270 degrees. Okay, so it's moving 3/4 of that circle around. Okay, so it's doing 3/4 of a revolution. Okay, so let's figure out how far it moves in one full revolution. So in one full revolution, it would move the same as the circumference. So go ahead and write what your circumference is. So your circumference is 2 pi, and since the little second hand is 5 inches long, then the tip of it's moving, right? It's going to be 5 inches, so we're going to have 10 pi. So in a full revolution, it would move a distance of 10 pi, and that would be in inches. So for us, we do 270 out of 360, which you guys have said was 3/4 of the revolution. So we're going to multiply by 10 pi. Which reduces down to 15 pi over 2. Okay, so that's the number of inches that is moving. Now in this section, I'm going to ask you lots of things. I'm going to say, what is the speed in inches per second, and so on. How do you think I would find that if I asked for the speed in inches per second? What would I have to do now? Exactly. It took a total of 45 seconds to move that much. Does that make sense? You would take your answer and you would divide by 45. Okay, so I always want you to kind of think logically through the problem. Think about how many revolutions you have, what fraction of a revolution, how much it's moving in an entire revolution, and so on. All right, so it says we know that the speed of a moving object is speed equals distance divided by time, right? Distance equals rate times time. So speed is the distance divided by time. If an object is moving along a circular path with radius r, the linear speed and angular speed are given by the arc length divided by time for the linear speed. That's going to be something like inches per second, right? Miles per hour. And so on. But when we talk about something called angular speed, we use a funny symbol. It looks like a W, but it's actually omega. Yeah. So omega equals theta over t. And the units here, if you're talking about an angle divided by time, it's going to be things like radians per second or degrees per second, right? Degrees per minute. So radians per second, degrees per minute, and so on. Okay? Because we're talking about how much the angle is moving. Okay, so the easiest way to do these problems is to kind of like use common sense, to think about them. So linear speed is how many inches, feet, meters, etc. that an object has traveled, usually along like the edge of a wheel or something, per unit time. And angular speed is how much the central angle has changed per unit time. So I remember when I took physics in college, my teacher always did lots of experiments, which most physics teachers do, right? So what he did is he took a bike tire, and I meant to borrow a bike tire from Mr. Crawley. So he took a bike tire, and then he told us to pretend that there was a bug on the edge of the tire. Okay, does Mr. Crawley do this too? Yeah. And then as you spin it, this bug is traveling pretty fast, right? It's traveling a certain number of circumferences, a certain number of revolutions all the way around per second. Okay, so you're trying to find out how fast it's traveling in, miles per second, meters per second, feet per second, whatever. Okay, but then if you talk about what angle it's moving, right? One revolution would be 360 degrees per whatever. So if it takes 5 seconds to make a full revolution or whatever. But then you talk about a bug in a different location. So what if the bug is in here? Okay, so it's like closer on the spokes of the tire. Okay, so if the bug moves, so it was on that outside here and now it's on the inside. What do you guys think? Does it go faster or slower for its linear speed? So when you talk about your feet per second, what do you think? Slower. It's actually slower. And you can kind of think about it because it's not, if you talk about its circumference now, its circumference is smaller, right? But it's still traveling that same number of seconds around. Okay, so when you're a kid, if you get in the merry-go-round and you're not very brave, like I was never very brave, and you're on the merry-go-round, you sit in the center of the merry-go-round. Does that make sense? Okay, but if you're one of the brave ones, you're like on the outside. You're the one pushing the merry-go-round, right? Because you're going around super fast. Does that make sense? All right, but what about the angular speed? Would the angular speed for those bugs be the same? Yeah, it's actually the same. Okay, you're still traveling the same, 360 degrees per whatever time. Does that make sense? Okay, so you kind of have to think about it a little bit. All right, so the circular mobile above a baby's crib makes 5 revolutions per minute. So what is the angular speed of the mobile in radians per minute? Okay, so sometimes it really helps to think about your unit conversions. Okay, so if we have 5 revolutions per minute and we want to change it to radians per minute, let's just do it just like you do in chemistry. So if you have 1 revolution, how many radians are in 1 revolution? Talked about this yesterday. In 1 unit circle, how many radians do I have? 2 pi. That's all you really need to do, because now when you cancel your revolutions, you have radians per minute. So see how unit conversions can help you with these as well. So you're going to get 10 pi radians per minute. All right, so basically what we did there is we did the formula. We just did the conversions. We took our central angle, which is 2 pi radians, and we divided by our time, which was 1 minute per 5 revolutions. See how it gets kind of tricky when you do the, well, I shouldn't write it that way. So if I have 5 revolutions per minute, how long does it take for 1 revolution, I guess? 12 seconds. So you would need to divide by that fraction of a second, right? So if you divide by that fraction of a second, right, then you end up multiplying by that fifth. Multiplying by 5, I mean. Do you guys see what I'm saying? I'm saying like 2 pi divided by 1/5 is the same as 2 pi times 5 over 1. Okay, so see how unit conversions can help simplify that process. All right, so next up. So how fast is a toy that's 9 inches from the center traveling in feet per minute? So we have a toy that's 9 inches away. So in 1 revolution, that's the same as 1 circumference, right? How far is it going? So we have our circumference is equal to 2 pi times 9. So it's going to be 18 pi, but make sure you're keeping track of your units. All right, so we're going to use that information. We're going to use 18 pi inches in our conversion. Okay, so it's doing 5 revolutions per minute. So let's start with what we were given. But 1 revolution is the same as 1 circumference. So if you need to write that conversion, you can. 1 revolution is 1 circumference. But 1 circumference was how much? 18 pi inches, right? So think about what your units are right now. You have inches per minute. What do we want? Feet per minute. So what else do we need to do? Yeah, we need to convert it into feet, right? So we have inches. So we want to put 12 inches on the bottom and 1 foot on the top. Have you guys all done this in chemistry? You guys know what I'm doing, right? Okay. It's the convenience of pre-calc versus algebra 2. You guys have all had it now. Oops, I'm just moving every single thing except for what I want. I don't know what's going on. Let me just erase this. It's like canceling half my stuff. So circumference. All right, and then we had inches, 12 inches and 1 foot. And then I tried to cancel my inches and inches. All right, so what we get is 5 times 18 pi and then all divided by 12. So you can reduce down a little bit. 18 and 12 reduced by 6. So 15 pi over 2 is in feet per minute. All right, does that make sense? And then see how fast is the toy 6 inches from the center traveling in feet per minute. So you would do the same process. So you'd say, okay, well, I have 5 revolutions every single minute, right? And it doesn't matter where you're located on the mobile, you're still going around every minute 5 times. All right, and then you can continue to simplify. So a lot of times I leave off the circumference thing. I just think of 1 revolution as being a circumference. And so I say, okay, well, 1 revolution is the same as, in this case, 2 pi times 6 inches. That's the circumference. And then again, I want feet per minute. So I have 12 inches per 1 foot. So it cancels and we get 5 pi feet per minute. So a little bit slower. And the other one was like 7.5. Okay, are you guys understanding this process? Those of you that have had physics before, you're probably like, woo, I like this section. But those of you that haven't are probably like, whoa, this is too much. So if you need help, let me know. All right, so this next one. So George Washington Gale Ferris Jr. created the first Ferris wheel for the World's Columbian Exposition in Chicago. It was 264 feet in diameter, so this is pretty huge. And it took 20 minutes for 2 full revolutions. So find the angular speed of the Ferris wheel in radians per minute. Okay, so if it's taking 20 minutes for 2 full revolutions, how long does it take for 1 revolution? So when I talk about something in radians per minute, 1 revolution is the same as 2 pi radians. So it takes 10 minutes for 2 pi radians. So we're going to say 2 pi radians per 10 minutes. That's how long it's taking. So it reduces down to pi over 5 radians. So if you wanted to write this with your unit conversions, you would start out and you'd say, okay, I get 2 revolutions per minute per 20 minutes, right? That'd be really, really fast. And then you multiply. So you have 1 revolution is the same as 2 pi radians. And then you see, okay, I'm in radians per minute now. Does that make sense? So it would still work out to pi over 5. So it's pi over 5 radians per minute. So the linear speed, so we want to know how fast along the edge are you going? Okay, so we need to find the circumference whenever we talk about the linear speed. So our circumference is going to be 2 pi times r, or you could use another formula. What else could we use for circumference? What's 2r? Diameter, so we could do pi d. Okay, so in this case we get pi times 264, so 264 pi, and it's in feet. So let's find what it is in feet per minute. And I guess I didn't specify. Usually I'll try to specify. All right, so our speed is we go 2 revolutions every 20 minutes, or you could write 1 revolution every 10 minutes. So we have 1 revolution, and 1 revolution is composed of 1 circumference, right? So our circumference is 264 pi feet. So when we do this conversion, do we get what we want? Do we get feet per minute? We do. So we convert. So we have 264 pi over 20. And we reduce our fraction. So it reduces into 66 over 5 pi.
Why is it 264 over 10?
I used, oh yeah, that's right. I forgot my, so it should be 264 over 10. So it should reduce the 2 and the 20. That's why I should have done that at the beginning, right? You're right. So can you write your name on the board so I don't forget? So 264 over 10 which reduces to 132 pi over 5 feet per minute. Okay. All right, and number 3, over the course of one day, what is the angular displacement? So the distance traveled from the starting point. So whenever you talk about this displacement, quick physics lesson. Okay, with my cross-country runners, I will always say, run out 3 miles and then come back the other 3 miles, right? So they run a total distance of 6 miles. Does that make sense? But when you talk in physics about displacement is how much you move from the starting point. So really, their displacement would be 0. Does that make sense? Because they went out 3, and then they came back, -3. So 3 plus -3 gives you 0. They're back at the starting point. Does that make sense? So whenever I use the word displacement, I kind of wrote it in there. Distance traveled from the starting point. So at the very end. So you want to find the distance between the starting point and the end point. So of the second hand in the clock in radians. So what is its angular speed? So its angular displacement. Ooh, maybe I shouldn't use the word displacement then. So angular displacement would be what? Let's use the word distance. Now I've confused myself because that's not what I wanted this to do. So what is the distance, the angular distance traveled? So in one single day. So for the second hand clock, or the second hand on the clock, how many rotations does it make? What do you guys think?
3,600 times.
Okay, close. Okay, not 36.
24 times.
So for every single minute, so for every minute, the second hand goes around 360 degrees, right? Does that make sense? Okay. So you need to do 24 times what? 60. So you're going to do 24 times 60. Is that what it is? 1440? Yeah. All right. Now we need to talk about how many degrees that's going to bend. So that's how many times it's gone around. So this is the number of rotations. All right, so the angle then is 360 times 1440. So it'd be 518,400 degrees per, I don't know, what would we say? Well, I guess I don't need per, whatever. So I'm just saying how many degrees has it rotated, right? So then what about its angular speed then? So it would be that value, 518,400 degrees per what unit of time? Per day, exactly. Now what if I asked per second? What would we have to do? No? How many seconds are there in a day? 3,600. So divide by 3,600, right? 60 times 60. Oh, that's true. You would. All right. So and then so that's per. What are we right now? So that's per day. No, now I'm confusing myself. I need to write out all my. So now divide by 24. And then divide by 24. Hours in a day. All right, so what do we get? 6? So 6 degrees per second. Okay, is that what we think that a second hand does? Yeah, so if you have 360 degrees and there's how many tick marks in there? There's 60, right? Doesn't it make sense that it'd be 6 degrees every single second? Like going from 1 second to 2 seconds to 3 seconds, yeah. So that is correct. All right. Oh, I repeated that one. So next up. So a gymnast on a high bar travels 3 full rotations in 2.75 seconds. What is his angular velocity during this time? Okay. So we have 3 revolutions per 2.75 seconds. So if we talk about an angular velocity, maybe we want it in, let's say, radians per second. So find in radians per second. So if we want to do that, then we need to change our revolutions into radians. So we have 2 pi radians. What if I wanted degrees? What would I use instead? 360 degrees for 1 revolution, right? So we multiply. So we have 3 times 2. You get to put the pi in if you want, divided by 2.75. So it's 2.18 repeating pi. But if I go ahead and I multiply the pi in, since it's already a decimal, I get 6.854 radians per second. It's pretty fast. All right. So the next ones are like pulley problems. Okay, these ones are kind of strange when you first look at them. Have you guys done these before? Have you done pulley problems? Yeah. All right, so a simple pulley with a radius of 10 inches is used to lift heavy objects positioned 4 feet above ground level. Okay, so we're going to have a radius of 10 here. And the pulley, I guess I didn't word this very well, is positioned 4 feet above ground level. So given that the pulley rotates 120 degrees, find the height the object is lifted. Okay, so if we have this circle and we lift 120 degrees, we want to know how much this distance is right here. Does that make sense? Because when you're turning the pulley, that's how much the entire like string or chain or whatever is pulling it. As you move, that distance is the same. Okay, so I'm going to do 120 over 360, and I'm going to multiply by the circumference. So I have 2 pi times r, which is 10 inches. Because I'm moving it like a third of that circle. I wish I had like a pulley so I could show you guys. So basically, if I move this distance here, like 120 degrees, and I'm moving that piece of string up that much, that's reflected in how much you're pulling it up. Okay, it's moving that same distance. So from here to here is the same distance as from here to here. Okay, so we need to find basically the arc length. Okay, so when I do that, I get 1/3 times 20 pi. So I get 20 pi over 3. All right, the 4 feet is really kind of irrelevant. You just want to make sure that it's not more than 4 feet. Because if you're moving it more than 4 feet, then it's now just like on the ground. Does that make sense? You pulled it all the way around. So it's not going to do much. All right, so we're pulling at 20 pi over 3. And this is all in inches. So it would be, if I find that answer, it'd be like 20.944 inches. Okay, do you guys understand the pulley thing? Like what's happening? Okay. Trying to think of a real life, something we could do with that. All right, and then the area of the sector, this is a really easy formula. We talked about this when you guys were doing your PSAT prep. It's just like the arc length formula. You just want to think about what portion of the circle you have. So if you have, 75 degrees and you're trying to find this area here, then you would want to find the circumference and then multiply by 75 over 360. Or not circumference, the area, sorry, and multiply by 75 over 360. So this is going to be theta over 360 times the area of a circle, which is pi r squared. All right, so yesterday I talked about how the arc length formula was r times theta. So you could write it with an L or an S. The book uses an S, as long as you were in radians. Okay, so let's talk about why that is. So the arc length formula I gave you was theta over 360 times 2 pi r. But theta in this case is in radians. Okay, so if you wanted to change something from like radians to degrees, remember we did a conversion factor? So what we would do is we would multiply, so we have degrees. So we want to do degrees. Is that how I want to do it? No. Now I got to think about it. Because this is degrees over degrees, let me think. So I would have to multiply it by, so let me write this, hang on. So I get pi r theta over 180 degrees. So I'd have to multiply by 180 over pi. And what happens is the 180 and 180 cancel, and pi cancel. And so that's why it works when it's already, like if you're in radians, if theta is already in radians, that's why just r times theta. So let's do the same thing here. So if we were in, so we had theta over 360 pi r squared. Then if we multiply, I guess think about clearing the pi. That's kind of the key, I guess. We want to put pi and 180 like that. So things would cancel. We get a 2 there. So we'd have theta and then r squared over 2. Oh, the r cancels? Do I have an r?
Oh, no,
I think,
fine.
yeah, so we get like that. So it could be different, but remember the best thing to do is probably just do it that way. Like think about it in degrees, because I think that's the most straightforward formula.
And radians, 1, 3, 4.
Yeah. So if you're already in radians, then it kind of cancels some things already. All right, so a sprinkler system is set to spray water over a radius of 35 feet and to rotate through an angle of 180 degrees, or 140 degrees. Okay, so we have 140 degrees, and it's not going to spray anything past that. So have you guys ever seen the sprinklers where it's like filling? I don't know, if you run, you always run into sprinklers where you're like trying to time it so you don't get all wet, but it's going to do like that. Does that make sense? But it only goes a certain distance, so that's like why it's part of the circle there. It can only spray out a certain distance. Okay? So we're trying to find this area that it's spraying. So we're going to have 140 over 360, and we multiply by the area, which is going to be pi times 35 squared. Okay, so you get a really big number. I haven't multiplied the pi in yet. So I had that, and then multiplying by pi, yeah. And it'd be in square feet. So 1,496.620 square feet. Does that make sense? Okay. All right, so I know that section was tricky for those of you that haven't had physics, but now if you take physics next year, you're gonna be like, oh, I know this. So kind of a catch-22. It's like whatever you take first, that's when it's gonna be hard. When you take it the second time, you'll be like, oh, I totally get this.